So I'm Abbie Stevens, and I'm doing a PhD at University of Amsterdam, and I'm going to tell you a bit about what I'm doing that on. So I'm going to be telling you about neutron stars and black holes and the weird space around them. Black holes you've probably heard of, but neutron stars maybe you haven't. David talked a little bit about neutron stars. So the story is going to be in two parts. First is going to be what neutron stars and black holes are, and then second, how we learn about them and how we know the things that we know. So for part one, what are they? Neutron stars and black holes come about in the final life stage of a normal star. So when a star dies, it turns into one of three things, depending on how big it is. A white dwarf, a neutron star, or a black hole. So if it's kind of the size of our sun, maybe a bit less, maybe a bit more, up to maybe 8 times as big as our sun, it'll turn into a white dwarf. And most stars fall under this category, including our sun. A white dwarf is roughly the size of the Earth, but it has almost as much stuff as our sun in it. So it gets pretty dense. If the star is a bit more massive than that, up to about 20 times the mass of our sun, and you'll notice I say mass of our sun a lot. Things are so big and heavy in space that astronomers just use the amount of stuff in our sun as a unit, because measuring it in grams or kilograms just doesn't really make sense. So if it is up to 20 times the size of our sun, the star will go supernova, and what's left over is a neutron star. The neutron star is very dense. It's only 25 kilometers in diameter, but it has 1.5 to 2 times the stuff of our sun crammed into 25 kilometers. Its average density, which is how compact it is, or the amount of stuff per volume, is on par with an atomic nucleus. And its inner core is denser than an atomic nucleus. So this is stuff that we cannot possibly study on Earth at all. To get an intuition for this kind of density, imagine taking every person on Earth, all 7 and some odd billion people, and squishing them into a 1 centimeter cube. It hurts. That's the kind of density of a neutron star that we're talking about. And this extreme density causes the neutron star to warp space-time. So Albert Einstein's theory of general relativity is our leading theory of how gravity works. And it says that matter tells space-time how to bend, and then the fabric of space-time tells matter how to move. And both parts of those are important. So in this framework, a neutron star is massive enough and dense enough to bend space-time by a decent amount. And then the curved space-time causes the light and matter that's near a neutron star to behave in really strange ways. So let's talk about a neutron star's gravitational field. The acceleration due to gravity, which is a way of measuring the strength of a gravitational field, at the surface of a neutron star is 100 billion times stronger than at the surface of the Earth. So if you drop your phone on Earth from 1 meter up, or if you're Dutch from 2 meters up, it hits the ground in a couple of milliseconds when you drop it on Earth. But if you did that from 1 meter off the surface of a neutron star, it would drop so fast from the strong gravity that it would hit the surface in 1/billionth of a second. Also, your phone would break. The work that you do against gravity hiking Mount Everest on the surface of Earth is the same as what it would take to hike 1/1000th of a millimeter on the surface of a neutron star, assuming that you have a magical spacesuit that allows you to not be totally pancaked to start with. And then black holes are weirder than that. A black hole is the remnant of a massive normal star, more than 20 times the mass of our sun, or even bigger. And a black hole is what's left over after some supernova. Some black holes are 6 to 10 times as massive as our sun, and these are the small ones. We call these stellar black holes, or stellar mass black holes. These ones are a few kilometers across in diameter, typically, maybe 2 or 3 kilometers. The first black holes that were discovered by LIGO, the gravitational wave detectors last year, those were 30-something times the mass of our sun. And when they combined, they made a black hole that was about 60 times the mass of our sun. So this is getting pretty big and pretty heavy. Because remember, there's a lot of stuff in the sun to start with, and then 60 times that. And then there are supermassive black holes at the centers of galaxies. And these are millions or billions of times the mass of our sun. Sagittarius A star, and it's about 4 million times the mass of the sun, but it's only maybe 30 times the size of the sun. And as we've maybe figured out, black holes, they're more massive and even denser than neutron stars. So they bend space-time even stronger than a neutron star. And then again, the light and the matter behave really strangely around them. But unlike neutron stars, black holes don't have a hard surface. So the size that I'm referring to here is the event horizon. This is the point, or rather the surface, of no return, where the gravity is so strong that not even light can escape. So while black holes have stronger gravitational effects, there reaches a point where we have no hope of ever knowing what is inside it. So in some senses, neutron stars are actually more interesting to look at. How we learn more about neutron stars and black holes. So part 2, how do we learn about them? Black holes and neutron stars tend to exist in binaries with normal type stars like our sun. So you have a neutron star or a black hole and a normal star, and they're pretty close together and they orbit around each other, kind of like the Earth and the Moon orbit around each other. But the gravity of the neutron star or black hole is really, really strong, as we talked about. So if it's close enough to the normal star, then the outer stuff of the normal star becomes more gravitationally attracted to the neutron star or the black hole than it is to its own star. And then this star stuff falls towards and swirls around and onto the neutron star or the black hole. And this process of draining the normal star and feeding the black hole or neutron star is called accretion. And accretion is a very powerful astrophysical process. Forms a disk around the neutron star of the black hole. Almost you can think of it like the rings of Saturn, but a lot thicker with a lot more stuff in it. And there's a lot of friction within this disk, and that makes it really hot. Now, when anything is hot, it shines energy. So for the human body, we shine most of our heat energy as infrared radiation. Like with infrared cameras or night vision goggles, people glow really brightly because of the infrared heat. The sun is hotter, and it shines most of its heat energy in visible light. And this accretion disk of hot star stuff, the inner part that's close to the black hole of a neutron star, is so hot that it shines most of its heat energy as X-ray radiation. The same energy that your doctor uses to take pictures of your bone. And this X-ray hot part of the accretion disk is also the part that is sitting in the bent space-time of that strong gravitational field close to the black hole or neutron star. So we're talking within hundreds of kilometers of the black hole or neutron star. So if we study this X-ray radiation, it can tell us how this stuff is moving and behaving in a strong gravitational field. We can't just take a picture, because this interesting region around black holes and neutron stars is both very small and very far away. So if you take the typical distance for one in our galaxy, it would be like trying to resolve the width of a human hair on Mars at closest approach. We can't do that. So on the sky, this looks like a single dot or a single pixel. But the X-rays aren't constant. They flicker and wiggle and vary in brightness, and these variations are fast, tens to hundreds of times per second. If you look at a particular black hole or neutron star with an X-ray telescope for a few hours, you can build a variability picture of these flickers and wiggles in X-rays, and some interesting patterns emerge. There's noise that can look flat or like weird lumps, and we think that this is from stuff in the accretion disk gently flaring in brightness as it moves towards the neutron star or black hole. There are then pulsations in some neutron star systems, like David talked about, and these are very regular brightness changes. Neutron stars have really strong magnetic fields, thousands of times stronger than anything that's ever been created on the lab on Earth. And the magnetic fields can cause this lighthouse effect, where you see regular brightness flashes when the north or south pole is pointed towards you. Some of the pulsations happen hundreds of times per second, so you have a neutron star that's 25 kilometers across, spinning hundreds of times per second. Neutron stars that show pulse light like this are called pulsars, and Claudia's going to tell us a story about the discovery of pulsars in the last session. Then, for both neutron stars and black holes, there are quasi-periodic oscillations. So they have a bit of a period, but they're not very precise. They're not quite periodic and not quite noise. But you could almost think of it like a changing heartbeat in the accretion flow. There are lots of different types of quasi-periodic oscillations. So the combination of quasi-periodic oscillations is like a noise, and the noise in the variability picture is almost like a fingerprint. I have one colleague who has a nearly photographic memory for variability pictures. So you can show her one and she says, oh, that's that black hole from 2010. Or you show her this other one and, oh yeah, that's that neutron star from 2002. And we think that the quasi-periodic oscillations are telling us about a hot, fluffy flow of star stuff that's piling onto the neutron star or black hole, and it's wobbling around from being in this really strong gravitational field. X-rays that are coming from this hot star stuff that's around neutron stars and black holes, and it's sitting in curved space. So by looking at these X-rays, they can tell us more about what black holes and neutron stars are and how they make matter do weird stuff. I have some 3D printed accretion discs with me that you can play with during the break.